I'm going to be solving 2 or 3 questions from chapter 9. Yeah, thank you. Now in the class. Um, so this is the first question. It says, this is question 933 in your textbook for the 5th edition. Consider a 15 centimeter by 20 centimeter printed PCB that has electronic components on one side. The board is placed in a room at 20 degrees Celsius. The heat loss from the back surface of the board is negligible. If the circuit board is dissipating 8 watts of power in steady operation, determine the average temperature of the hot surface of the board, assuming that the board is A, vertical, B, horizontal with the hot surface facing up, and horizontal with the hot surface facing down. Take the emissivity of the surface of the board to be 0.8 and assume the surrounding surfaces to be at the same temperature as the air in the room. Evaluate air properties at a film temperature of 32.5 degrees Celsius and 1 atmosphere pressure. Is this a good assumption? Um, let me start putting down this the values we have. So we have a circuit board and it has a hot surface, and we have to neglect what is happening on the other side. So it's a board, and then we have this to be 15, 20 by 15. So I'll say the length is 20 centimeters, and that is 0.2 meters. And then we have the okay, and then the board is placed in a room. The room temperature is 20 degrees Celsius. The heat loss from the board is negligible. Board is dissipating 8 watts. Power is 8 watts. Emissivity is 0.8. Okay, so the first question says that we should find the surface temperature on the hot side of the board. The lines, and then just okay, so, okay, let's say this is the bottom of the board and this is our hot side. Okay, when it is vertical. Now to evaluate the first part of this question, we have to take the following assumptions. One, steady operating conditions, as usual. 2, the air is ideal. Okay, we'll take the air to be an ideal gas with constant properties, so we don't have to worry about that. And 3, the local atmospheric pressure has been given to us as 1 atmosphere, and we also know that the heat loss from the back is negligible. So these are our assumptions. Now, I want to approach this question in a different way, different from the way we usually do it. Okay, I'm going to start from the final equation that we use to find our surface temperature, and just work back from it and just see what we get. Now, we have been given the emissivity for this situation. So it means we're going to take into consideration the radiation from the hot side of the board to the walls, to the surfaces of the room. So the total heat We can evaluate this by considering the total heat loss. Okay, the total heat loss from the board. And to do that, we can use the um, heat transfer equation. But this, we are going to take into consideration both the convection heat loss and the radiation heat loss. Now, for the convection heat loss, we have that to be equal to this expression. And then we'll add the radiation heat loss equation also. Which will be Ts is equal to 4 minus the surrounding temperature is equal to 4. Now, we're trying to find Ts, okay? So if we can find all the other parameters, then it becomes just a straight algebraic operation. We can find A, the surface area. We've been given the parameters to be able to find that. T infinity, we have been given the room temperature, okay? We have been given the emissivity. We also know the surface area. We know our Stefan Boltzmann constant. And we can also make an assumption for the surrounding temperature. We've been told in the question to take the temperature of the surrounding walls to be equal to the temperature of the room. So if you look at this, the only other parameter that we have to worry about in order to find Ts is H, which is a convection heat transfer coefficient. Okay. And in this situation, for natural convection, H is affected by buoyancy and gravity. And I'm sure you've done that in class where you came up with a Grashof number, which takes into consideration those two things that affect natural heat convection. Okay. So we have an expression for H. H can be found by this expression, right? This is a constant property. We can find this from tables, right? We know what L is. We've been given the length, which is the height of our board in this case, the characteristic length. I'll show you that in the textbook. Then the only other thing now is to find a Nusselt number. Now, if you take a look at table, let me share my screen with you right quick. Table 9.1. Okay, so this table right here, you can find the characteristic length based on the geometry of the or the shape of the problem you're working with. And in this case, in the A part of the question, we're trying to find Ts for when the board is in the vertical position, just like this. So our characteristic length is L, the height of the board in this case. And we can first of all try to find a Rayleigh number just to know which expression to use, or we can use a general case, okay, which it also gives us a more precise result, okay, for the Nusselt number. So this is the expression that we can use to find a Nusselt number. And then if you look at this equation here, you have the Rayleigh number and the Prandtl number. Those are the two other things that we have to find. So we can find this, but in order to find this, we have to find Rayleigh number and Prandtl number for the problem, okay? Then to find this, the Rayleigh number is just equal to Grashof number multiplied by Prandtl number, right? For the question. This is a constant, this is another constant property that we can find from tables. So to find this, we have to find Grashof number. And this is also a formula that you can find from your textbook. And this is equal to this expression right here. Okay. This is gravity. This is gravity. This is the volume expansion coefficient. This is our T infinity, which we already know. I'll come back to this. This is L. We know what this is. This is the kinematic viscosity. We can find this is another constant property that we can find from tables. Now, Ts in this case is the value we're trying to find. Now, we can run into trouble here if we don't analyze this. Now, we have to make an initial assumption for what Ts would be from constant from what we know about the question. Okay. And then when we make the assumption and we'll find out TS in the end, we'll compare the values and see if it makes sense. And that is what it means when the question says, um, ask if the initial guess is good. Okay. So the only other thing we have to find here now is the volume expansion coefficient, which is the inverse of um, the film temperature in kelvins. Okay, so beta is equal to 1 over Tf in Kelvin. So if we find all this, we can then evaluate what Ts is. So I'm just going to write out all the constant properties that we have to find. We have to find the value of K from tables. We have to find a Prandtl number. We have to find um, the kinematic viscosity. Yeah, so those are the three things that we have to find from tables, and then we can go ahead and evaluate the rest of it. Now, the question says that we should assume our film temperature to be 32.5. Now, remember in the last few weeks, we have been solving questions and we always take our film temperature to be an average of the two temperatures that we've been given. And the question says that we should assume that our film temperature is 32.5 and 1 atmosphere pressure. Okay, so we can then evaluate what beta is. So that's beta is equal to 1. Remember that this is the inverse of our film temperature in Kelvin. Okay, so it will be 32.5 plus 273 Kelvin. Okay, and this will give us the value 0.003273 Kelvin inverse. Okay, now this film temperature TF, which we are given as 32.5, is also equal to Ts plus T infinity divided by 2. Right? We know that we've been given this, and this is what it is equal to. So in order to find what T infinity will be for this expression, we just multiply this by 2 and then subtract from, sorry about that. We've been given the T infinity to be 20 degrees, which is the room temperature. So if we subtract this from this expression, we'll find what our assumed Ts will be, just so that we can evaluate our Grashof number. So the Ts that we are assuming or approximating in this case will be 2 multiplied by 32.5 minus 20. And you find that to be 65 minus 20, which gives us 45 degrees Celsius. And that is a Ts that we are going to be working with. Okay. Now, the other properties that we can find are We know that G is 9.8. G is 9.8 meter per second square. T infinity is 20 degrees Celsius. We have our initial Ts to be 45 degrees Celsius. We know our length to be 0.2 meter, which is just the height of the board, which was given as 20 centimeters. From tables, we know that kinematic viscosity. Now, this is the kinematic viscosity for air at 1 atmosphere and 32 degrees, 32.5 degrees Celsius. Okay, that is the film temperature that we're working with. So if you go to table A15 in your textbook, you can find that you can find these values. Okay, you might have to do a bit of iteration to find them, but V will be about 1.631 times 10 raised to negative 5. And you find the thermal conductivity to be 0.02607 degrees Celsius. Okay, and the Prandtl number is 0.7275. This is for air at 32.5 degrees Celsius and 1 atmosphere. Okay, and we already evaluated our volume expansion coefficient to be 0.03273 Kelvin inverse. Okay, so we have everything we need to go ahead and start computing our values now. Okay, so Grashof number is, I'll just use the formula which I put down here. Okay, so it's G, which is gravity, 9.81 meter per second square, multiplied by a value for beta. And then TS, we have our initial TS, which is 45 minus 20. Remember that this is a temperature difference. So there is really no need to convert to Kelvin, because if you add 273, it just goes away. But this is in Kelvin, okay? And multiplied by the length, which is 0.2 raised to power 3. All these divided by the square of the dynamic viscosity, the kinematic viscosity, sorry. Okay. So if you evaluate this, you get 2.4137 times 10 raised to power 7. Okay. Now our Rayleigh number is this value multiplied by Prandtl number, which you already have from tables. Okay. So it's 2.4137 times 10 raised to power 7 multiplied by 0.7275. We get this value to be 1.756 times 10 raised to power 7. Okay. Then the next thing is to key it into the Nusselt number, the formula I showed in the table 9.1. Okay. So this is going to be a big equation. We have 0.825 plus 0.387 multiplied by the Rayleigh number 1.756 times 10 raised to the power 7 raised to power 1 over 6. All these divided by 1 plus 0.492 divided by Prandtl number 0.27275 raised to the power 9, 16, and then all this raised to the power of 8 over 27, and then all this squared. Yeah, that's a big equation. So you get that value to be 36.78. Okay. I'm running through this. I already computed these values. I'm running through it so we have enough time to look at the second question today. But you can, on your free time, try to compute this and see if we have the right values. So we now have our Nusselt number and we can now compute the convection heat transfer coefficient, which is, we already have here to be K over L multiplied by the Nusselt number. We have gotten this from tables. We have L already. So we get that to be 0.0267 divided by 0.2 meter multiplied by 36.78. Okay. This answer is now 4.794 percentages. Okay, so now that we have this value, we can now go ahead and compute what the actual TS will be. Okay, so we have gotten everything we need to find this now. We have this and we have every other thing here. So I'll just go ahead and put that in and see what we get. And remember that we have been given a Q to be 8 watts. Okay. So once we equate that, we can find our value for TS. So 8 watts equal to H, which is 4.794 multiplied by the area. So I have not computed the area. So the area here, the surface area, is simply just 0.2 multiplied by the breadth of the PCB, which is 0.15, convert 15 centimeter to meters. And this gives us 0.03 meters squared. Careful with your decimal points. If you're doing this calculation by head, don't forget about this decimal place. So that's our area, and multiply that and into Ts minus T infinity. Now, remember I said something about being careful with when you're dealing with radiation, okay? You have to convert these to Kelvin. You also have to do that conversion here, but just as a good practice, whenever you are working with an equation that involves radiation, convert everything just so you don't run into trouble. But if you take a look at this, if I say plus 273 here and plus 273 here, if I open the bracket, 273 just goes away. Okay, so I'll just say Ts minus T infinity, which we have to be 20 degrees Celsius. It's going to be Kelvin. Now it's Kelvin. I know it's Kelvin because I've opened the bracket and 270, both 273 and the two cases have gone away. They've canceled out. Okay, so that's that for the convection side. So I'll say plus our emissivity is 0.8 multiplied by the area, which is 0.03 meters square, and then multiplied by Stefan Boltzmann constant, which is 5.6 5.67 times 10 minus 8. And then into this is where we're going to add Ts plus 273 Kelvin raised to the power 4 minus 20 plus, let me write this down here. Okay, minus 20 plus 273 Kelvin raised to the power 4. Okay. So we can now find the value of Ts. Okay. Now, we can go ahead and decide to do this algebraically, but I'm going to show you how you can do it in Mathematica, Wolfram Mathematica, just in case you encounter a more nasty looking equation in the future, you can easily put it in Mathematica and just find the result. So if you, let me share my screen quick. Okay, so if you don't have this, there's a student edition, which is free. All you have to go to the website and use your ISU email, and you can get a free version of this program. So we can key in this value and just find the value of TS. Now we know that. So what I'm going to do is I'm going to bring 8 to this other side so that we have the whole equation equal to 0. So it becomes easy to find the value of TS. Okay. So I'm just going to say solve. And the first value is 4.794. 4.794 multiplied by, I'm not, the units are not going to appear here. Okay, just for us to do this better. So TS, I'm just going to call it T minus 20. We have that. Okay. And then plus, let me not forget to put the multiplication sign here just in case. Okay. So plus emissivity, which is 0.8, multiplied by the area again, 0.03, multiplied by Stefan Boltzmann constant, which is 5.67, multiplied by 10 raised to power minus 8. Now all this will be multiplied by the difference between temperatures. So open this first bracket. I say T plus 273. Now all these raised to power 4. And then plus, I have the second expression here. This is 20 plus 273. All these raised to power 4. Okay. Now everything here, I'm going to subtract 8. This is me bringing 8 to this other side now. So I'll put a big bracket, put everything in one big bracket and just subtract 8. Okay, so we have our formula now, and I'm going to equate this to 0. Now in Mathematica, just like many other programming languages, if you want to equate to 0, you use 2 equal to signs, okay? And then I'm trying to find T. Okay, once you do this, so we have our answer, okay? You can see there's a mistake somewhere. 7.94. Hold on, let me just quickly find where the mistake is coming from. Okay, let me put these in brackets and see. I think I'm making a mistake here. Oh, okay. This is where the mistake is coming. Okay, this is supposed to be a minus sign right here. Okay, I hope you can see this. This is minus. Okay, so I'm just gonna copy this and paste, and well, there you go. So I already solved this, and I know what the answer is. That's why I can tell that it's a mistake. So I made a mistake by putting plus here instead of minus. Okay, so we have four values for t, right? Because I mean, t was raised to the power of 4. Well, if you take a look at the values we have gotten here, we have t equals to minus 841. This is degrees Celsius, by the way. Okay, minus 841 degrees Celsius. Does that make sense to you? Okay, this looks unreasonable. This is a complex number. This is another complex number, the complex pair. And then look at the final result we get here. T equal to 46.62 degrees Celsius. Okay, this makes better sense, right? Because we made the assumption that our temperature is 45 degrees Celsius, and we have gotten this result. Okay, so I'll go with this result as our answer for this first part. Okay, so TS for when the board is vertical is 46.62 degrees Celsius. Okay. Now we're running out of time, so I'll just quickly go to the next part. So for B, we have that. What's the question again? The board is now placed horizontally, okay, with the hot side facing up. So just like we did this assumption here, we can start this same question by saying, okay, we can write this expression to find TS, but what changes in this situation? Okay, we still have the same surface area. No, we have a different surface area this time, but we still have the same emissivity, we have the same Stefan Boltzmann constant, we have the same T infinity, we have the same T surrounding, we have so the two things that change in this situation is the surface temperature, the surface area, and the convection heat transfer coefficient. Okay, and if this changes because we're going to have different values for our Nusselt number, and the Nusselt number is going to change because we're going to have a different Rayleigh number. Rayleigh number changes because we're going to have a different Grashof number. The Grashof number changes, so you can track it down until you start your expression by computing it from this point once again, until you get to this point where you're going to have different area and convection heat transfer coefficient. Okay. Now to start, I'll show you this table again. Table 9.1. Now look at this table. It says that when you have the geometry of the body under consideration, if it is in this position and the hot surface is on the top, then your characteristic length becomes the surface area divided by the perimeter. Okay. Now, remember that in this case, we just picked L to be L. In this case, LC is the surface area divided by the perimeter. And also, we can also find Nusselt number for this case by using this expression. Okay. So let us go ahead and compute this with this knowledge. And the next part is we're going to compute we're going to repeat the same calculations for when the board is placed in a horizontal position with the hot surface facing down. Okay. Okay, so LC for this situation is the surface area divided by the perimeter. We know the surface area to be 0.03 meters square. So we just have to divide this by the perimeter. Just add the two sides multiplied by 2. Okay, and if we compute that, we get it to be 0.0429 meter. Okay, so our relay number we know to be Grashof number multiplied by the Prandtl number. Prandtl number remains the same. Okay, nothing changes about that. The only thing that changes in this situation will be length. Our characteristic length has changed. Every other thing remains the same. We have this equation to be 9.81. Remember this equation? So I'm just going to multiply this and then multiply by the Prandtl number. Okay. So 9.81 multiplied by beta, which we got to be 0.003273 K inverse, 45 minus 20, and then multiplied by 0, the characteristic length, the cube value of the characteristic length. All this divided by the kinematic viscosity, we have to be the same thing. Okay, and then multiply all this now by the Prandtl number just to get the relay number. So in this case, our relay number is 1.728 times 10 raised to the power 5. Okay, we can do the same thing. The only thing that changes in calculating our Nusselt number now is um, um, the relay number, right? Because we have this to be we have that big expression. Oh, hold on, no, let me show you that table again. We have gotten our relay number, and which is raised to power 10. Sorry, this is raised to power 5. Let me just quickly show you that table again. So we have our relay number to be 1 times 10 raised to power 5. Now look at the range that you're shown in the textbook. Now, if your range falls between 10 raised to power 4 and 10 raised to power 7, then this is your Nusselt number equation, okay? Which is the case for us here. If we had this a different range, we use this other formula here, but this is the one we have to use. So it is Nusselt number is equal to 0.54 multiplied by the relay number raised to power 1 over 4. Okay. So if we calculate that, we'll get it to be our Nusselt number in this case becomes 11.01. And from here, we remember that H is equals to K over L multiplied by this. So our H becomes 6.696. Okay. So if we go back into Mathematica, you notice that the only thing that has changed here now is the area. No, our surface area remains the same. The only thing that's changed is our H value. Okay. The only thing that changed in this case was the characteristic length and our H value. We have computed our H value here now. So if I go back into Mathematica, all I have to do is copy this equation once again. I'll copy this and paste it down here. And before I press enter, I'm just going to go ahead and change my H value. It is no longer 4.79. It's now 6.696. Okay, that's the only thing that changes in our expression. And by the time I say enter, we still have this very huge value here. We have the complex number pairs, and then we have this value, and that is T surface for this condition, 42.5705 degrees Celsius. Okay, so by now you should have noticed a trend. Okay, so if we're going to compute the next one, which is for the case where it is horizontal, but the hot surface is facing down, we're going to repeat the same procedure. The only thing that changes here now is we're still going to have a characteristic length that is AS over P, but this time when you compute your Rayleigh number, you are going to get a different value. This is the formula to find the Nusselt number for this condition. Okay, we're no longer using this formula, so we're going to have a different Nusselt number, but we still have the same characteristic length. So if you compute all that, you get it to be, oh my God, we're so out of time. Okay, and our Rayleigh number in this case becomes 1.728 times 10 raised to the power 5. Our Nusselt number becomes 0.27. Oh, hold on. Our Nusselt number becomes 5.5. And then H in this case is 3.34. Okay, every other thing stays the same. So I'll go back into Mathematica and put this new value of H. So I'll come back here now. I'll just copy this once again and then paste it. And before I press enter, I'll just change the value of H. We have a new value of H, which is 3.34. So once again, we have this weirdly large number. We have the complex number pairs, and then we have the value of T. So Ts for this situation is 50.74 degrees Celsius. Okay, so we have now found our values. Let me check just to confirm that we have the right answers. So if you come to the textbook, scroll down to here we have our solutions. So 933. Okay. So for the sixth edition, which I'm using, is question 938. Okay, so our solution here says 4, 6. Yes, we have the right answers. Okay, so let me just write them. Let me just write them out here just to show you. So for this configuration, we had a TS to be 46.6. For this configuration, we had TS to be 42.57. I'll just say 42.6 degrees Celsius. And then for this configuration, we had TS to be 50.7 degrees Celsius. So just take a look at this and just do kind of an intuitive analysis. Does this make sense? If you look at it, I think from what we know about buoyancy and gravity and how natural convection works, this actually makes sense. It makes sense that this in this configuration, when T infinity is 20 degrees, this has the lowest surface temperature because we know that once the because of the density of the air around this area, okay, it interacts with the cold air around it, and buoyancy takes effect, okay, it has that upward force on it, so the air rises. It produces that rising effect. Okay, so it makes sense that this will be the most, this will have the best cooling effect. Now, this will also have that, but I would imagine that it would take more, to take much more to have the air around this area to be displaced by the fluid surrounding. And then this just looks catastrophic. I mean, because the air, the hot warm air around here is trying to rise. It's just rising back into the board, which is why we would have such temperatures compared to this. Okay. So I thought we are going to have time to solve a second question, but I think we're just 3 minutes away from the end of this class. So do you have any question about this? I hope it's clear. Are there any questions? Okay.
I don't have any questions.
Okay. So next week, I think I'll probably just continue from here next week. And if you have any questions at all about any of the assignments that we've done so far, if there's any solution you don't understand, I posted the solution for assignment 1 and 2. I'm going to post the solution for assignment 3 and 4 also before next class. So if there's any of this you don't understand and you don't know why you didn't get it correctly, you can just come prepared to ask me those questions next week. Okay. So yeah, so that's the end of the recitation class for today. And have a nice rest of your day. See you guys next week.
Thank you.
Have a good day.
Yeah, thank you.